Hello students, this is the last part of chapter 3, and in this section you do want to bring out your molecular modeling set, so get your models out for sure. And what we're going to talk about are conformations. Molecules are going to want to adopt the lowest energy conformation to minimize repulsion between electrons and strain in a system. So the first kind of notation we're going to look at is something called the Newman projection. And then we're going to visualize that as well through an energy diagram. It'll be fun, you'll see. So if we just consider ethane, you have two carbons. Each of those are sp3 hybridized. You have this tetrahedral geometry. Take a look at your model set and play around with it. Just notice that there's free rotation around the bonds. One, the molecule can move in space. Just looking at this and thinking about repulsion between electrons, and again, atoms are made of electrons. What is the best conformation? What do you think is the lowest energy conformation that this ethane molecule would want to adopt? So if I look at this head on, I can stack the two white hydrogens. So if you haven't built your model yet, the black balls are carbons. You have a bond, mine is gray, and then I use white balls for the hydrogens. You can stack your white balls right on top of each other. That is the most defensive interaction because they're close together, you have more repulsion. If you can move them out of the plane, then that's a little bit better. So sometimes that's hard to visualize. What I want you to do is make this structure here. This hydrogen is straight up and you're looking down the C1-C2 bond. So think of this left section, this propeller section, is this upper H is like the head of a person. And then he has two legs. And if you're looking straight down, there's a leg to the left and a leg to the right. We're going to look at this head on and draw it in a circle here. So that upper H is this upper H here. You're looking head on to that carbon, which is where my C1 circle is right now. And his legs are to the left and to the right of you. Right behind that is C2. You can't see it in this molecule here, in this projection here, in this Newman projection. If you look straight on, it's hidden behind the first carbon. And this guy now is upside down. His head is straight below, but behind. And then his legs are splayed out to the left and to the right. So I'm gonna just show you here. What you guys should be looking at is this. So here's your ethane molecule, but if you look straight down carbon 1 and carbon 2, the carbon 2 is back here, but you can't see it. I like to hold the front one constant, and you can see I can rotate this around. This is the most defensive, where all the H's are stacked right on top of each other. We call that eclipsed right on top of each other. Just think of like solar eclipse. The best is where they can be staggered. So the staggered conformation relieves some of that repulsion and gives it the best orientation. Okay, so that's shown here. What I'm showing here is the lowest energy staggered conformation. You also have an eclipsed conformation that I also showed. And what we can do is find out just how offensive that is. There is an energy cost to rotate around the ring. It's not just freely rotating. You have to have enough energy because it's hard to get past these hydrogens. This is actually one of the easiest systems you can imagine. If you had like a methyl group or a butyl group there, that ends up costing a lot more. But what we could do is just do some calculations, find out that the energy to go between these staggered and eclipsed is 3 kilocalories per mole. Say this is the lowest energy conformer. I'm going to just say that's a baseline of 0. This high energy one is 3 kcals. So we can calculate that. And what we realize is the only thing that's offensive here versus that staggered conformation is that there are 3 eclipsing HH interactions. And that means if you take the 3 kcals divided by those 3 eclipsing interactions, each of those HH eclipsing interactions must cost you 1 kcal per mole. So here's another way you can look at it. Here's a staggered sawhorse projection. That might be easier to visualize. And here's the eclipsed. Notice the H is straight up, eclipsing this H straight up. Similar to here, it's straight up. And it's drawn off to the left a little bit in the Newman projection, but it's really straight behind it. Just to let you know, I'm starting to use kcal energies, and you also can use kilojoules. So sometimes you'll see both used depending on the book you're using. Let's take a look at butane. So now draw a structure. You could draw a structure for butane, but also build it. Build a butane molecule with your modeling set. And you guys play around with it, rotate bonds, and you guys tell me what is the most stable or least stable. So let me just show you. Here's my butane, 4 carbons in a row, all saturated. You can rotate all sorts. You can rotate around the CC bonds, the molecules moving around. The lowest energy one is all staggered versus this one, where you can literally hear the hydrogens bumping into each other. So the lowest energy is, if I look straight down, these carbons, C2, C3, is the ones where they're opposite each other. Where the methyl group and this methyl group are opposite each other, we call that anti. So we're going to look at some Newman projections of butane, looking down the C2 and C3, holding this top methyl constant, and we're going to rotate around the ring. So I'm going to just show you that on the slides, and then we can look at it again in the model. So here's our eclipsing interaction. You can see how offensive that is. The H's literally bump into each other. We call that steric strain. The anti-conformation, which I draw here at the end, it's anti-periplanar because the methyls are opposite each other, periplanar because they're not exactly in the same plane, but there's a CC plane and then the methyl groups. So this is the lowest energy. We'll give it a baseline of 0. As you move, and you guys can go ahead and move it, so you can start at the anti and then move your back methyl group 60 degrees. You can get to one that's eclipsed here with an H. You can move it up 60 degrees and you can get one that's called gauche, where the methyls are somewhat close to each other, but not fully eclipsed on top of each other. So these methyls should be right on top of each other. This is the most offensive. This is going to cost you a lot of energy, 4.5 kcals per mole. It's because you have the steric strain, these guys bumping up against each other, and there's something called torsional strain as you pass each other in this eclipsed interaction. So the most offensive is this. The next most offensive is the other eclipsed, where it's methyl H eclipsed. And then the gauche. The gauche will cost you almost 1 kcal per mole. And then the anti. So I want to show this to you again. We'll start this time at the fully eclipsed. So again, you have your molecule here. You're looking straight down the C2 and C3, where my fingers are. And then eclipsed is where the 2 methyls are right on top of each other. That's methyl-methyl eclipsed. You also have this HH eclipsed and HH eclipsed here. So what I'm going to do is hold the front constant and just move the back. Just 60 degrees. I get this gauche interaction. So I get this gauche between methyl-methyl. That's going to be 0.9 kcals. If I go another 60 degrees, now this methyl is eclipsed with this H, And the top methyl is eclipsed with an H, and you also have an HH eclipsed here. Another 60 degrees, and you get your favorite lowest energy anti or anti-periplanar methyls as far apart as possible. Let me just recap about the types of strain. Just strain in general. This increases the instability of the molecule. It's just forcing two things that don't want to be near each other together. And so that increases the potential energy of that molecule. So higher in energies means more unstable. You could think of it as it's like a rubber band, and if you let go, you release that energy. Okay, and this is due to electron repulsion. Two types of strain I highlighted were torsional strain. This is due to electron repulsion between groups as they pass each other during a bond rotation. So this can be relieved with a bond rotation. As we can see, if I have something with the torsional strain from an eclipse conformation, I could just go to staggered and relieve that. Steric strain, also called steric hindrance, is due to, again, electron repulsion between atoms. These aren't directly bonded to each other, but they're near each other and they can even bump into each other. We saw that with the gauche interaction. It's nearby, and these methyls are close enough where it's a problem. There's repulsion. Know these interactions here and the energies associated with that. Let's apply this to an energy diagram, because this is what it's all about. You guys should be able to draw and reproduce an energy diagram based on these conformations. Here I show from anti going to eclipse to gauche, and the other Newman projections for butane. Energy increases as you go up. So the lowest energy, we'll say as the baseline of 0, is anti-periplanar. As I move the methyl group, and this time I'm moving from bottom to an eclipsed, H-methyl eclipsed, H-methyl eclipsed, and HH eclipsed, I increase in energy 3.8 kcals. Then I can relieve some of that strain and I get to a gauche. But the gauche still has some, this is your gauche here. Methyl-methyl is your gauche interaction. There is some offensive interaction, so that it'll cost you 0.9 kcals. If I move the methyl group another 60 degrees, I get to the worst methyl-methyl eclipsed with two other eclipsed. This is the highest energy. Some people also call this syn-periplanar, 4.6 kcals. Keep going, you can relieve that somewhat back to the gauche. And then you go back, cycle through the eclipse interaction, and then anti-periplanar again. Okay, practice this sort of Newman projection, looking at a molecule, just a structure of a molecule. Practice that using your models and translate that to an energy diagram. You should be able to draw those. All right, you guys, that ends chapter 3.